Hello everyone, welcome to the course Data Structures. This is N. Tulsi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. Let us see the today's overview of course regarding trees concept. Here we are going to discuss about what is the introduction to tree. Then we will be seeing about what is the terminology under trees. Then we will look into the applications of trees, and at last we will be seeing how to represent trees, representation of trees also. And let us look into the height. Here, total number of edges that lie on the longest path from any leaf node. Any leaf node to a particular node is nothing but the height of that node. Here we are going to find the height of the node as well as the height of a tree also, as we have seen in the degree also. For degree of a node we have find it out, and degree of tree also we have seen. In the same way, when you are going to represent the height of a node we will see, and height of a tree also we can find it out. Okay, and when you are going to see the height of all leaf nodes, always be 0. Why? Because you don't have the node extended for that. Because of that, we are going to represent with 0. And you can see here if I want to find the height of a node, how we are going to find the height of a particular node? You need to check the total number of edges that lies on the longest path from any leaf to a particular node. From leaf we need to move on to that particular node. How many edges are there, that will be counted. Now you can see here, suppose I want to find the height of a particular node, you consider B. This height, it is representing it as 2. How we can say it is 2? I need to start from the leaf node, from here. This is the edge I am going to have, right? This is the edge which it is representing between these nodes. Now I need to start from the leaf node. This is one edge and this is another edge. These are the two edges where we have. So that the height of this particular B is 2. In the same way, if I want to find the height of A, then again we need to start from the leaf node. Leaf node is from here, not from here, right? We need to start from the leaf node to the node which you want to find it for that particular node, right? That is, this is one edge, K2G, and this is another edge, and this is another edge. Totally we have 3 edges are there. That's why the height of this A is 3. If I want to find the height of a tree, the same, which is having the highest value, right? Which is having the highest longest path from leaf node to the root node, then that is representing the height of a tree. Height of a tree is nothing but the root node which I am going to have, and this height of a tree is nothing but, here we have, this is the height, and in the similar way we can find the height of each and every node. In this way we can find it out. For the leaf node it is 0, and for the remaining nodes from leaf node to that particular node, if you are going to check for E, if I want to find the height of that particular node, then you have only one edge, so that you are going to get it as 1. And like this way we can find it for the remaining. And what is the depth of the tree? Here the total number of edges from root node to a particular node. In the in the height we have started from leaf node to the particular node, but here when you are going to see the depth, the total number of edges from root node to that particular node is going to be given as the depth of that node. And in the similar way, depth of the tree also we can take it from the total number of edges from root node to the leaf node, in which the longest path we are going to consider. And if we can see this tree, here depth we are going to take it from, suppose I want to find the depth of this A. For depth of root node is 0. In the previous case, height of leaf node is 0, and here the depth of root node is 0. This is representing the depth. And from there you are going to start, from there to the leaf node. And what is the depth of B? The depth of B is from here to the leaf node we need to move. That particular node to the leaf node, from top to bottom, right? And previously we have gone from bottom to top. This is representing the depth of B. Depth of B is nothing but from here to here. Parent node to that root node. This is 2. Depth is 2. And if I am going to look into that, here the terms level and depth are used interchangeably. We can use in place of depth level, we can use depth in some case. And if we can see for this particular tree, what is the depth of B? This node to this node. Depth of B, that is the particular node to this leaf node. If you are going to see, the depth is 1 for this one. In this way, we can find it for the leaf node, and same way we can find it for the root node also. For the depth of root node, it is always 0, and height it may be differs. Height of leaf node is 0. And like this way, you can check for the remaining cases also, which I have placed here. And the next definition terminology where we can see is subtree. In a tree, each child from node forms a subtree recursively. Suppose if I am going to have a tree like this. This is a tree, right? And in this we have subtrees, that is left subtree and right subtree like this, right? These are going to be formed recursively, and every child node forms a subtree on its parent node. Every child forms a subtree from its parent node. This is based on the parent node. It is going to form the subtrees. This is another subtree, and this is called left subtree, and this is called right subtree. And the next where you have is forest. A forest is nothing but a set of disjoint trees. As we have seen in the starting of the tree representation, we have represented two separate trees, and we have said that is not satisfying the property of a tree, and we can say now that as a forest, right? This is one tree and this is one tree. These are two different trees which are disjoint, and so that we can call it as a forest. And the next one we have path. In a tree data structure, the sequence of nodes from one node to another is called as path between two nodes, and length of the path is nothing but the total number of nodes in that path, right? If you can see the example here, if I want to find the path of from A to J, how I can move A to B and B to E and E to J, and whatever the nodes that was present in that will give you the length of the path, right? And if I am going to find it for C to K, and the length is 3. We need to count the nodes, not the links between them, right? And then if you are going to see the applications of trees, this can be used to represent in different hierarchies, mainly in file structure and dictionary directories. We are going to see, when you are going to see, if you have seen in your system, we have created so many files. In that file I am going to store, suppose I am going to have Chitra. In that I am going to have one more folder related to PPS, and in that folder I am going to store some nodes related to unit 1. Under unit 1 again I am going to store some PPTs, some nodes content, like this way. If you can see, this is the hierarchy where our files are going to be stored in our directories, right? This way, this is the path, or this is the root way where it can store all our data. And for faster searching also, we are going to use the concept of trees, and how that will be, because when you are going to see about the binary search trees, based on this concept we can search whether the given element or given number is present in the given list or not. This technique will be used. The binary search will be searching the element very fast. And we have advanced to that. We have B trees, and B plus trees are also used to implement indexing in databases, right? This indexing is nothing but you have some index values, something like 0, 1, 2. Based on that indexes, how fastly you are going to access your data. And this is mainly used in our database, that is database management systems. There will be knowing about what is B tree and what is B plus trees. And then this is where the structure of B trees will be. You can able to find it out here. These are the indexes. Based on the indexes, how we can access the values. And another one where we are going to use the application of trees is a syntax tree used in compilers. That is, if I am going to write some statement related to syntax, we have if statements, we have if else statements, something like that. Suppose I am going to write some expression like this way. E plus E by E into E. This is one expression which I am going to write, right? And this expression, how I am going to represent in the syntax tree representation, like this way. Here E is nothing but the ID, identifier, and A plus is nothing but the operator, right? And based on this, it is going to represent in the syntax tree format. Based on some rules, this tree can be constructed. And mainly in routing algorithms, in computer networks, we come across these trees in routing algorithms, and then used in building heap data structure. As we have discussed in the previous session, heap sort, there it is going to be used in constructing or building of a heap data structure also. These trees are going to be used. And last comingly, the representation of trees. As whatever we have represented the trees in this way, in the heap format or hierarchical format, can we able to represent the same while doing our programming? It is not possible to represent in the same format, right? So that as we have discussed in the heap data structure itself or heap sort itself, we are going to store the same data in terms of an array representation. But here we have some more ways to store this or represent the trees, right? And what are the different ways we are going to represent the trees? Let us see. We have three different ways of representing trees. One is list representation. List is nothing but the linked list representation. And the second one is the left child right sibling representation, right? This one we will see, look into that, how we are going to represent. And degree 2 representation. These are the three different ways where we are going to represent the trees. List representation we have already discussed, but let us see how we are going to represent it. And if you have given a tree like this, and how we are going to represent in terms of a list. Here you can see this is a root node, and for this you have 3 child nodes out there. So that we are going to make the connection of 3 nodes like this. This is representing B, this is C, and this is D. And for B again we have child nodes. And for that we are going to extend those 2 nodes are there, E and F. These 2 nodes are going to be make the link. That means we are going to store the address of the child nodes into the parent node like this. And if I am going to see about this C node is having only 2 nodes, C and G, right? At the end of the node, if you don't have any children, we are going to end up with this like this way. Otherwise we are going to represent with null also. And let us look into D. For D, I have 3 children, that is 1, 2 and 3. 3 children has been represented, but for I and J, I don't have any children. That's why we are going to end up here itself, I and J. Those 2 are siblings, that's why we are making the connection and end up here. And but when you are going to see about E, right? From B, I have E. From E again, I have K and L. From B, I have a children. And for E again, I have children K and L. So that we are going to make the connection like this. And for D, I have H. Yes, from H, I have M. So that we need to represent like this. Okay. And this is nothing but the list representation. And the same thing where we are going to represent the list representation with the parenthesis, which it is representing its children as well as the parent, all these things. And another one is left child right sibling representation. Left child right sibling representation. When you are going to see a node representation, a node consists of 3 parts actually, data, and we are going to store one part as left child and another part as the right child. Suppose if I am going to have a node like this is the data part and this is the left part and this is the right part, right? Now, how we are going to represent the same thing in terms of left child right sibling representation? Let us look here. Here, the data is A, right? And whatever the siblings for this node A, all should be come as the right part of it, right children for it, right? This is a left child, right? This is a left child placing as it is, and remaining C and D are the siblings of this with a B, so that we are going to make them as the right of it. Okay. Now, if you can see the next one, E and F, right? E and F are siblings, but E is the left child placing as it is, and F becomes the right sibling for it. And if you can see K and L, here also the same case. K is the left child and L is the sibling of it, so that we are going to make it as a right child. And here we have C and G is there. C is already sibling and G is the left child for it, so that's why we are going to place as it is. We are not doing any right sibling for it. And for D, you have H. The siblings of H are I and G, so that we are going to make it as the right siblings, and M is the left child placing as it is. Okay, like this way we are going to represent the left child right sibling representation. And the last representation where we have is degree 2 representation. Here, to obtain this 2-degree representation, what we need to do is simply we need to rotate the right sibling pointers to the into a left child right sibling tree clockwise by 45 degrees. When you want to represent this 2-degree representation, first we need to construct this left child right sibling, and we are going to rotate this one to 45 degrees. We are going to rotate, so that we are going to get the degree 2 representation. And refer here, 2 children of a node as a left and right child. We refer to the 2 children of a node as the left and right children. Notice that the right of the root node is empty. Here, when you are going to rotate this, you don't have the right part. We are going to have the left children. For that, we have the right siblings. That's all. But for the root node, you don't have any of this part. You don't find any right part of it. Only you have the left part. And the left child right sibling tree is also known as binary trees. Let us look into this, how you are going to do this one. Yes, as we have seen in the previous diagram, this one, by referring this, just to observe, we are going to rotate this one to this part, and when you are going to rotate this, here you have the right sibling of this one, right? For A, you have B, and for B, you have C and D, like this way. And for this one, you have E, and this is F, and this is K, and L is the right sibling. And for C, you don't have any change. And for D, you have H, and for this, you have I and J are the right siblings. And for H, you have F. Like this way we have, right? When you are doing this, when you are going to consider this one, this has to be rotated 45 degrees. Right, this has to be rotated 45 degrees, and after rotating 45 degrees, observe 45 degrees, which side they have to? Clockwise. Clockwise means this side we need to rotate. When I am rotating that, here observe, this one becomes the right child. B for C becomes the right child, and the complete part will be rotated, so that C and D will be rotated 45 degrees. You are going to get like this. And in the same way, whatever the right child, that becomes the right child of this one. K, for that K also the right child, you have L will be the right child for it, and G is the left child. And for H, if I am going to rotate this for 45 degrees, H, I, J, this becomes the right child, and M is the left child for it. When you observe the right part of this root node, you don't have any nodes. Why? Because when you're going to represent the left child right sibling, in this you won't get the right subtree of that particular node, right? Like this way we can able to construct the degree 2 representation. Yes, let us see the summary what we have discussed in this session. We have seen about the introduction to tree and what is the terminology we have come across. We have seen root, edge, path, child, parent, leaf nodes, and we come across so many depth level, all these things we have discussed. And applications of trees also we have seen how faster and what are the faster way of searching by using binary search trees, and how you are going to store your data in the hierarchical format, and how that is going to be stored in the directories or file directories, right? And then we come across the representation of trees, and the representation of trees we have seen about the three ways of representation: list representation, left child right sibling representation, and last is a degree 2 representation. Okay,